Welcome to class 3 of stochastic control and communication. So first I'll do a quick recap of what we saw in the last two classes. In the last two classes, we basically saw how to approach the problem of decision making under uncertainty, right? So um, uh, there are basically two things that happen when you have uncertainty in your system. One is you have this notion of risk, which intuitively everyone knows, but mathematically it's still an open problem on how do you define what is risk. And then the second problem is of information gathering, right? So how does information gathering play a part on how you choose how your decision making varies under uncertainty. So we'll talk about this today a bit, but before that, so today I'll just give us very quick recap of what all we have discussed under the subsection risk. So first we saw this one type of lottery where you had this 100 rupee entry fee, and then a biased coin was tossed, and with two-third probability. So you got heads with probability two-thirds, and you got tails with probability one-third. If you got head, you got 3 into 100 rupees. And if you got tails, you got 0 rupees. So here basically you had the average outcome was 200 rupees, whereas the payment to enter the lottery was 0 rupees. So because you had 100 rupees. So because you had your average outcome is greater than the payment, you you your innate decision would be to yes, I would join this. But same if you scale this to crores, then you would have 2 crore rupees average outcome, 1 crore rupees payment lottery. Even then your average outcome is greater than your payment, but then intuitively this feels more riskier than this, right? So here uh, so what we saw was uh, just comparing averages is not a good solution. We saw two more things where we compared worst case analysis, and we also did the max best case analysis. So we also saw that in these two cases also you're not comparing every you're not there is in these three types of comparisons of lotteries or decision makings, you're not incorporating risk in your decision making. So you're not comparing how much risky one process is to other or something like that, right? So then we came up this notion of expected utility theory. So what does expected utility theory say is that while comparing to distributions which you get from distribution which you get from your decisions, uh, here that is equivalent to, there will always exist a utility function such that you can compare these distributions by comparing the expected utility values. This is at d1 and expected ud2x. Yeah. So if you want to compare two decisions, just compare the expected utility at those decisions, and the form of the u function would be concave and increasing. There'll be concave and increasing functions. So there'll be something of the form of this, right? The rate of increase of that function will taper off. So this will be your x, or this will be your outcomes. This is your u of x. Okay. So even if you scale a problem linearly, which happened here. So you scale the problem from 100 to 2 crores. If you have a utility function which is concave and increasing, then you'll see that as you increase, the expected utility will not scale as much as your uh, entry fee, like your previous lottery has scaled. So yeah, so we were discussing all this. We were discussing what all the assumptions one needed to mm, for the existence of this function. And yeah, someone asked me to give me one more example for utility functions. So today, yeah, I'll explain about the Saint Petersburg's paradox. So this is one of the paradox which actually people solve this paradox using the expected utility theorem. Like that is one of the solutions where you can come up with a utility function to solve this problem. Right. So okay, I'll explain what the paradox is first. So you pay a fixed cost of X rupees. Okay. And you receive Y rupees. Now this is based on a coin flip. Okay. So you have a coin. You keep on flipping it until you get a tails. If you get a tails, you get money, right? Now, how much money is something that I'll tell right now. So if you get tails in the first attempt, you get tails, then you get 2 rupees. If you get heads and tails, then you get 4 rupees. So basically, you flip the coin, you get a head. Then again, you flip a coin, you get a tail. The game stops and you receive 4 rupees. And if you get 2 heads continuously, then you get 8 rupees. And this continues. Okay. So now the question is, what should be X? What is the value of X such that your decision is you would want to play this game? So what is the value of X such that it would be favorable for you to play this game? You guys have any guesses how to do this? Okay, so yeah, let's first go and calculate what is your average winnings that you get from this, right? So let's forget about text. How much money you get if you play this game once? What is the average you get? So this is an unbiased coin. And since this is an unbiased coin, you have tails with probability half and heads with probability half, right? Now, and each coin toss is independent of each other. Okay, so you get 2 rupees with probability half. You get 4 rupees with probability 1 by 2 square. You get 8 rupees with probability 1 by 2 cube, and so on. So this is your expected winnings. Winnings is Y. So this is your expected Y. This is the amount that you're getting. Expected amount that you're getting if you play the game once. So this boils down to 1 plus 1 plus 1 so on to infinity. And this value is infinite. Now you see here is the paradox that your expected winnings you get is infinity. That means for any finite value of X, you can play this game and win, right? But what happens is people usually, if you play this game, you don't win. Like if X is really high, then you start losing the game. Like you will lose the game very quickly. but that doesn't come up here if you just take your decision based on the averages that you've calculated. Right. So, okay. So, why is this happening here? I'll, we'll do some more. So, suppose uh, you play a game 64 times, right? Then what you'll see is so now your outcomes are basically these things like 2, 4, 8, and so on. Like your outcome space is 2, 4, 8, 16, 32. At each time it doubles. And now the probability distribution of your outcome, if you want to play the game, is basically half, 1/4, 1/8, 1/16, and so on. Okay. So you see here that 2 you get with the probability half. So if you play the game 64 times, on an average, 32 times you will get 2. Similarly, 16 times you'll get 4. Similarly, 8 times you will get 8, and so on. Now, if you do this for okay, so let's do this one. For 4 times you'll get 16, 2 times you'll get 32, and 1 time you'll get 64. And I think one is remaining. One time is remaining. This one time is basically everything which is equal to or greater than 128. So this one time we'll just fix it to be 128. This is an approximation. We'll just approximate that everything is greater than 128 is 128. We are doing this because the probability of now you are in the probability of 1 by 128, 1 by 256, and that which is very small number. So we are incorporating everything as 0. And here you get it as 512, the total winnings in 64 times, right? So you actually get 8 rupees. You win 8 rupees on average. This all is on average if you play this game 64 times. Similarly, now if you do it for 256 times, on an average, I'm not writing down everything, but you'll get 2,560 winnings, and that is 256. That is 10 times, 10 rupees. So basically, you have jumped a huge number of game, but your average winnings have not gone really up, have not increased that much. So if you play 2 power s times, then you get s plus 2 winnings. This is an approximation that you can make to just come up with an utility function that you can say that, yeah, like you can come up with a utility function to define this, to not solve this problem, but to uh, remove the paradox that you have created in this St. Petersburg paradox. So what it says is uh, you basically have to your utility function needs to be of the form log t to the base 2 plus 2 of this form. Like if your utility function is of this form, then uh, so your decision that you'll be making should use this utility function and take the expectation of this utility function, and then based on this you should come up with a decision of what is the finite value of x that you can uh, play with. So basically that answer, I'm not solving the whole problem, I leave it as an exercise for you. It comes out to be, I think, something around 16 something. Yeah. So this was just one of the example on decision making under uncertainty, where it is where it shows that you don't take your decisions just by comparing the average outcome that you get. You actually have to find a way to map your average outcomes to your average utilities. So how much utility am I getting for that outcome? If you are able to find that uh, utility function, then Yeah. Okay. So next, I'll be going into the role of information in the system. How does role of information affect your decision making, right? So I'll give an example. So today we'll just deal with two examples, one for risk that we have seen here, and one for the role of information. So in the example, we'll take a system with a scalar state. So you have scalar state, but you're observing the state at two different times. So you have x1 at time one, the state is basically u0 plus w0, and you're also observing at time two where x2 is x1 plus u1. So here x1 and x2 are your states of system at time 1 and 2. u0 and u1 are your decisions. w0 is the noise or randomness that happens in the system, right? Now the question is find u0 u1 to minimize expected mod x2. So yeah, one more assumption is you know some statistics of the noise that you don't know what the value of the noise is, but you know the statistics of the noise says that W0 belongs to -1, 1 with probability half each. So basically it is a random marker distribution. So W0 takes the value either 1 or -1 with probability half. So now finally your problem boils down to minimize expectation mod x2 such that you want to find u0 u1 such that x1 equal to u0 plus w0 under this dynamics of the system. X2 is equal to x1 plus u1. So we'll substitute this dynamics in here and we'll see what the objective function is. So this is expectation of mod x1 plus u1. This is equal to expectation of mod u0 plus u1 plus w0. And since the only randomness in all of this is in w0, this expectation is over w0. So, and w0 takes discrete values, so you can expand this expectation as minimize with probability half. W0 takes 1, so you have mod u0 plus u1 plus 1 plus half mod u0 plus u1 minus 1. And now you don't need to write the dynamics because you have incorporated all the dynamics in your objective function. And there's a function in u0 and u1, and u0 is and u1 is what you want to find out, right? So now here we need to make an assumption on what information is known and when is it known. So now, do we know? Uh, uh, So here u0 and u1 are your decision variables. So after, do we take first, do we give the decision u0, then do we get to know x1, and then we get to choose what u1 is, or we give it a we don't have this intermediate step. You're asked to just find the vector u0 comma u1 such that this is minimized. So in this in the first assumption, what we'll do is we want u0 u1 without knowing about x1. Okay, so in that case, minimizing, so we want to minimize this, right? So this is basically -1 and 1, and you have u0 plus u1. And the distance between, now u0 you can plus u1 could be anywhere. It could be in between -1 and 1. It could be greater than -1. It could be less than -1. It could be greater than 1. So I'm just taking one case, case 1, where u0 plus u1 is in between -1 and 1. Okay, so this is basically u0 plus u1 plus 1, and this is u0 plus u1 minus 1. And the other cases are if u0 plus u1 is less than -1, then you'll have this is u0 plus u1 plus 1. This whole thing is u0 plus u1 minus 1. Minus 1, 1, u0 plus u1. And then this is u0 plus u1 minus 1. This is u0 plus u1 plus 1. And now from the plots, you can see that in case 1, this whole term, half mod u0 plus u1 plus half mod this is basically equal to 1. And for case 2 and case 3, the objective function is greater than or equal to 1. So for these two cases won't come, only this case will come. And so the optimal value is 1. But what is the u0 and u1? U0 and u1 just need to be between 1 and -1, right? So you just choose u0 and u1. You just choose u0 and u1 such that the sum of those lie between -1 and any optimal value, and the optimal value you get is 1. Now, if I change the assumption, for which I get how I get the information. So instead of deciding both u0 and u1 at the same time, uh, what if I first get to decide what u0 is, and then I am able to see what x1 is, and then based on what x1 is, I get to choose what u1 is, right? So here what we are doing is we are u0 and u1 are decided in a sequence. So first u0 is chosen, then u1 is chosen based on the observation x1. So then we want to minimize mod x1, mod x2. So here, before substituting what x1 is, this is already known because after choosing u0, you will know what x1 is. Because x1 is already known, you can just choose u1 to be minus x1. That's it, you're done. And you can choose u0 anything. And now if you see here, the minimum expectation of mod x2, u0 and u1 such that um, yeah, x1 equal to u0 plus w0 and x2 equal to x1 plus u1. Now the optimal solution for this is 0, where u0 could be anything and u1 is basically minus x1 because you know x1 here. You have an observation in the middle. So you see the same problem of trying to, you have these dynamics, these are your system dynamics. And you are minimizing expectation of mod x2 and you want to find this control variables u0 u1. If you have two different assumptions, the first one is where you give the vector u0 u1 without any knowing anything about x1 in the middle, or you decide u0 u1 in a sequence where you know what x1 is. You see that uh, this second assumption, we are able to perform better and we are getting good optimal solutions there. And these both are directly different. So when you're making decisions in under uncertainty, um, yeah, so information gathering plays a important role in it. And are you doing a sequential information or are you doing everything at once? Plays a major role in how you, what are the optimal decision that you have taken, and uh, the optimal solution also. So from this, what we'll introduce to is we'll introduce problems of sequential decision making. So I'll just give a brief outline of what problems of sequential decision making are. So it's basically minimize cost over a time horizon. That is, you're taking decision at each time step. And your time is discrete here. So that means you have k equal to 0, 1, so on to n minus 1. And this is finite. You have, so finite in the sense you have a finite horizon over which you can take a decision. So you have finite amount of finite dimension vector. Mm, yeah. And you have xk state of system at k. uk is your control action or decision at time k, and wk is your random parameter. So, okay, mathematically, how do you write this is your future state is a function of your current state, your current action, and some noise in the system. This function is known as the dynamics of the system. Now, when I say different information gathering scenario, we either know the closed form solution of this function or we know some statistics about this function onto how does knowing these three tell you what the future state could be. It could be in such a way that you don't know what x1 is given xk uk wk, but you might know some probability distribution function of xk plus 1 given you know what xk uk wk are. And the randomness only comes from wk. This is random. This is your decision that you get to choose, and this is the state that the uh, dynamics or trajectory of the system randomly take. And because of the randomness here, this will also be random, right? So what the end goal of this problem is that it is to minimize the total cost incurred from k equal to 0 to k equal to capital N. So hence you're solving a problem of minimize expectation gnxn plus summation k equal to 0 to n minus 1 gkxk ukwk. So this, this is your terminal state, and the whole thing, okay, this is your terminal state, and this whole thing is your terminal cost. And this whole thing is your stage-wise cost. Now, here in the information gathering thing, we have two cases, right? One where you take all the decisions beforehand, or you wait for the state to go each step and then you take decisions. So in the same way here also, you have two problems, two different directions you can solve this problem. One is the open loop problem, and one is the closed loop problem. So in the open loop problem, you decide u0 to un minus 1 even before the system evolves. And in the closed loop problem, you decide uk as a function of past history till k. You have this knowledge of what has happened before, so you know all um, basically x0, x1, x2, uh, and also u0, u1, u2, u3. So you have all this history of x0, u0, x1, u1, so on till xk. And based on all this, you take a decision on uk. So you usually take this as just the state feedback. So it's just f of xk. But here you do not know what wk is. So this is the randomness. This is uncertainty. The uncertainty comes from because you don't know what wk is, right? So these are your problems of sequential decision making. And um, one example for this is your inventory control. So in the next class, I will discuss about inventory control. Yeah, fine. Stop recording.